And then I'll just say really just a couple of words. And then maybe Nastya, you would introduce the speaker.
Sorry, sure, yes. Do you want to already connect, share your screen?
Oh, you want me to share my screen before he?
Well,
yeah,
whenever you want.
Yeah, I can do it now.
So okay, so I think so. We're live now. So let me just say a couple of words. So first of all, welcome everyone. It's so great to see so many returning faces that we saw in the previous Junior Global Poisson, and also so many new faces. So this is the second time we're doing this, and hopefully we'll continue doing this as the it'll be a recurring theme. Yes, I'm super excited that this is happening, and I'm really looking forward to all the talks and all the social interaction to get to know all of you, and make new friends and make new connections. Nastya, Ilya, Lena, do you want to add anything before we begin? Okay, then we
I think
can
that was a
begin.
no.
Okay, then I suppose we can begin. Welcome everyone. Okay, so Nastya, would you like to introduce the speaker?
Yes, sure. So our first speaker for the conference is Joseph Palmer, who will talk about Hamiltonian S1 spaces, symmetric integrable systems, and hyperbolic singularities.
Okay, great. So I hope everyone can hear me. Yeah, thanks for having me, and thanks for. I mean, I guess I'm the first talk. I get to be the first person to thank the organizers for putting this all together. I mean, it looks. I don't know. It looks like a lot of work. So, so it seems like everything will go smoothly. But anyway, I'm wasting my minutes, so I should start talking. Right, so I'm just going to report on some recent work I have joined with Sonia Holak, and well, and when I say recent, I mean I posted it yesterday to arXiv, so it has not yet appeared on arXiv, but it is posted in that sense, and it's really just about the relationship between four-dimensional S1 spaces and four-dimensional integrable systems. And so I'm going to go through a bunch of different results that people have in these directions and sort of show the new stuff we've figured out, I guess. So just to start out, for me, for this talk, M omega will always be a four-dimensional compact symplectic manifold. So the questions we talk about will make sense in higher dimensions and in the non-compact case, and in fact are very interesting. But for today, this is what I'll sort of stick with. And now I can say a few things that I think probably everyone knows. If you start with any real valued function on a symplectic manifold, it induces a Hamiltonian vector field by this equation. So some people put a minus sign, some people don't. That's not going to matter for me. And what we're going to be interested in are the situations where the flow of that vector field is periodic. So if the flow of that vector field is periodic, we say that F generates an S1 action. So it just means that F is the Hamiltonian function for the Hamiltonian action of the circle, S1. And I'll assume that the periods are all 2 pi, just to make things easier. So, right. So sort of our first object of interest is a Hamiltonian S1 space, which I'll just call an S1 space. And this is going to be a triple M omega J, where M omega is a symplectic four manifold, and J generates an effective S1 action. And so these have been studied in lots of contexts for quite some time. In particular, they were classified by a paper of Karshan in 1999, where you can associate to the triple a graph with some labels and extra data on it that sort of tells you all of the interesting features of the S1 space. I mean, it tells you everything about the S1 space, actually. And I'll explicitly describe this graph later, but I just want to introduce it for now. Sort of the other object that I'll be interested in are integrable systems. So an integrable system, again, in dimension 4, is just going to be two functions, J and H, and I can put them together into one function if I want, the momentum map, such that J and H Poisson commute and are also independent in the sense that their differentials are linearly independent everywhere. So probably all of you have heard of integrable systems. You know they're motivated by physics. You think of J and H as things like the angular momentum or the total energy of the system, and you want to understand sort of the dynamics. So that's sort of where they started, but now they show up all over the place. And in particular, sort of the nicest, to me at least, type of integrable system are the integrable systems that are called toric integrable systems. And so I'll describe this by saying that J and H both generate an S1 action. It's sort of equivalent to say that this capital F, putting the two J and H together, generates a T2 action, right? It's a Hamiltonian action of the two torus on a four-dimensional manifold. Right, this is, since J and H Poisson commute, they're two different S1 actions. Commute, therefore you get a torus. But I've written it, I've written it this way for a reason, right? To make it obvious the relationship that I have to S1 manifolds. But first, let me mention that these were also classified, this is even a little bit further back in the 1980s, by something called the Delzon polygon. That again, probably you've heard of, and also I'll say a little bit more in detail in a minute. But now we have enough sort of pieces to talk about the question. So it's pretty clear that if you start, it's extremely clear that if you start with a toric integrable system, so I'll call it M omega JH, if I just forget about the H, then what I'm left with is a Hamiltonian S1 space, M omega J. So going that direction from sort of the green circle to the purple circle is easy. You're just forgetting some information. And this is, these are pictures that I'll talk about in a minute. These are both supposed to be the second Hirzebruch surface. Somehow from the polygon that's related to the toric integral system, you can write down the graph that classifies the Hamiltonian S1 space. And so, of course, the interesting thing here now is going to be going the other direction. If I start with a Hamiltonian S1 space, what I'd like to do is see, can I find another function, this other H, so that I can extend it to a toric integrable system. And I was sort of talking about this in terms of the simplest possible objects just for now. But actually, I don't necessarily need to be interested in toric integrable systems. I can just look at some integrable system where the J generates S1 action and the H has some other restrictions on it, whatever you're interested in, really. And we'll have a couple different cases. So the questions I'm thinking about here. So the first question is, can I always extend an S1 space to a toric integrable system? So I have a Hamiltonian action of S1 on a manifold. Can I always find a sort of complementary Hamiltonian action of S1 to build a toric system? And I'll spoil the answer here, but we're going to get here in a few minutes. The answer to that is no. We can't always lift to something as nice as a toric system. So then the next natural question is, okay, well, can we at least lift to some integrable system? And this is sort of the question I'm going to be asking. Okay, can we find an H so that JH is an integrable system? And if we can find an H, what's sort of the nicest H, right? Restricting just to toric systems is too restrictive. You can't lift all the S1 spaces. So sort of my motivating question then is, what is the nicest class of integrable system to which all S1 spaces can be extended, if such a class even exists, right? It's initially not clear at all that you can always extend like this. Okay, so now I'll say things in a little more detail, but this is sort of the idea. So first I can describe the Poisson graph. So the way to think about the Poisson graph is that you just look for anything interesting in the S1 manifold, and that gives you some piece of the graph. So for instance, if you have an isolated fixed point of the S1 action, that becomes a vertex in your graph. The fixed points of the S1 action on a 4 manifold can also come in fixed surfaces. And these become what Poisson called a fat vertex. So sort of, I'll draw it as like a larger vertex that has extra labels on it: the volume of the fixed surface and the genus of the fixed surface. And the fixed points always have to either be isolated or in surfaces. And sort of the only other interesting thing about the S1 action would be the isotropy of points. And the way that these show up are in what are called ZK spheres. So a ZK sphere is a sphere that sort of rotates at k times faster than you would expect it to. So as you go through the whole S1 action, this sphere rotates k times instead of all of those points just returning to themselves once. And the thing you can notice is that, well, if you have a sphere that's rotating, the poles of that sphere are fixed points. So the ZK spheres connect isolated fixed points, which is why it makes sense for them to show up as edges in the graph, because they're connecting the different vertices, which are the isolated points. And so this would be sort of like a picture of what a Poisson graph would look like. And all of these pieces, we draw them according to their J value, right? We have this function J, the Hamiltonian. So here, in this picture, the far left image is a fixed surface of the sort of at the minimum value of J. And then at a bit higher value of J, you have an isolated fixed point. And then you have two isolated fixed points connected by a Z2 sphere. And I should mention that you don't draw Z1 spheres because that's not special, right? It's a sphere that rotates one time when it's supposed to rotate one time isn't like an interesting feature. So the ZK spheres have a lot of rigidity, but the Z1 spheres are really not, they don't show up in the graph. They're not as interesting. Okay, so that's sort of the background for S1 spaces. And now let's think about the toric situation. So when can we lift an S1 space to a toric integrable system? And I already revealed to you that the answer is not always, but I can argue that pretty quickly with some examples. So here's some review of things, again, people probably know, due to some results of Atiyah, Gilman Sternberg, and Delzant in the 1980s. Putting those results together, I have that given a toric integrable system, M omega F, the image of F of M, the image of the momentum map, is a polytope that satisfies certain conditions, and moreover, completely classifies the space. So I think this is pretty well known. There's just this one-to-one correspondence between toric integrable systems, let's say dimension 4, and Delzant polygons. And the requirements on what it means for a polygon to be Delzant is that it's a rational polygon, and there's also certain conditions on the angles that are allowed at the corners. So for instance, if I started with CP2, there's a standard action of the torus, just rotating the two components, and the image of that standard action is a right triangle. But what's great about this classification is not only that you get to use polygons instead of having to do geometry, but also that it's very explicit what's going on. By looking at this polygon, I can tell you what the fibers of this map, this momentum map, look like. The fibers over interior points, I'll call these regular fibers, are 2 tori. The fibers over points that are on edge of the polygon, I'll call these elliptic regular fibers, are circles. I mean, I guess I could call it a 1 torus. And the fibers over corners are just isolated points, and these are the elliptic points. And so this is sort of the picture of how things work in the toric case. So it's very rigid, and right from the polygon, you can sort of read everything off that you're interested in. And so now, suppose I start with a Delzant polygon of M omega JH. So it has 2 integrals, these 2 functions, and then I throw away the H, like we talked about before, and I'm left with M omega J. So this is, writing it as JH instead of writing it as like actually the joint momentum map of the entire torus sort of picks out a specific circle inside of that torus that is going to be the one that I use to induce the S1 action. And anyway, from the polygon, you can read off everything from the Poisson graph. I mean, it takes no time at all to go from the polygon to the associated Poisson graph. And I can sort of go through this dictionary here. So any vertex of the polygon corresponds to a fixed point of the S1 action, and therefore corresponds to a fixed point, a vertex of the graph. And any vertical edge of the polygon corresponds to a fixed surface. So in the previous one, I should have said like an internal vertex or something, because the vertical edges correspond to a fixed, not any fixed surface, a fixed sphere. And so in the Poisson graph, this will correspond to a fat vertex that is labeled with genus 0 and has its area equal to the length of that corresponding edge in the polygon. And finally, any edges of the polygon, if you write their slope as a reduced fraction of a over k, the preimage of that edge, right, the preimage of an edge of a Delson polygon should be a sphere. That's going to be a zk sphere, and therefore you get an edge with the label k. And this was all known to Koshon in her original paper. She was talking about these extending and descending problems already in the toric case then. So I'll do a really easy example. Let's start with CP2. So you can look at the polygon for CP2. On the left, there's a vertical edge, so that corresponds to a fixed sphere. Then you have two different edges that have integer height. And if they have integer height, they're not going to show up. So they don't correspond to anything. And then the far right corner is an isolated corner, so it's going to be a vertex. So the Koshon graph for CP2 looks like this. So any edges of integer slope are kind of interesting because they aren't sort of rigid. They don't have anything to do with the S1 space, maybe is the best thing to say. But let's continue making examples from CP2. So I'm going to perform an operation that I think probably most people are familiar with, and it's something you're allowed to do to Delson polygons. You can do what's called a corner chop. This corresponds to performing a blow up on the space upstairs, and there's sort of certain rules about the angle the corner chop has to be at. And so this is CP2 blown up one time. And so again, we can get the Koshon graph. We have a fixed surface, and now we have two vertices. So okay, that was good. Let's do it again. I can blow up on that left-hand side the same size again. And sort of, I'm indicating this by the fat vertex getting a little bit smaller instead of having to write the area label. And now I've picked up two fixed points that are sort of at the same j value. So now just looking down at the Koshon graph, there's no reason we can't keep doing this. So it's totally okay to make that fat vertex a little bit smaller and come up with another fixed point at that same level of j. But if you try and lift this to a toric system, you're going to have problems, right? Because the fixed points correspond to corners on the polytope, and you can't have three corners on a polytope all in the same vertical line, right? This is sort of the drawback of the toric case. So this cannot be extended to a toric system. Really, I mean, the best way to think about it, I think, is that all of the interesting features of the S1 space, everything that shows up in the Koshon graph, has to come from the boundary of the Delson polygon. So you can never have three interesting things happening at the same level of j. And this is one of the reasons why you can't always lift to a toric system. So what we'd like to do is come up with some integrable systems where something interesting can be happening in the interior. Okay, so now I'll introduce a generalization of toric systems called semi-toric systems. So a semi-toric integrable system, again, is m omega jh. And again, j is going to generate an S1 action, but h doesn't have to. So these are going to be, in fact, like a huge generalization of toric systems. But if I just let h be anything, the situation sort of gets too wild. So we require that all the singular points of the momentum map are non-degenerate with no hyperbolic components. So I'll explain what that is by essentially showing you every possible singular point in a minute. But at first, I should just mention that these were classified a little bit more recently, about 10 years ago, by Plyo and Vunagak in terms of 5 invariants. And one of these invariants is a polygon, sort of analogous to the toric case. So, right. So here's the image of a semi-toric system. It doesn't have to be a polygon right now. The toric systems, you automatically get a polygon. The semi-toric systems, you can get something that's not convex and has bent edges. And also there's sort of special points in the interior. And let me describe the possible fibers. So first of all, totally analogous to the toric case, if I take a random point in the interior, the preimage is a torus, that's a regular point. If I take a point on one of the boundaries, the preimage is a circle, that's an elliptic regular point. If I take a preimage of a corner, the preimage is just a point, and that's an elliptic point. But the sort of new situation are these marked points on the inside. There's certain points in the inside of the momentum map where if you take their pre-image, the torus is sort of degenerated. One of the cycles is collapsed, and you have what's called a focus-focus point. So a focus-focus point, I mean, what's interesting is it can show up in this context because it does admit an S1 action, right? It doesn't have both S1 actions. One of the cycles have sort of broken, but the other one it still admits. And so you can see that the focus-focus point itself, the sort of pinch point of this torus, is fixed by this rotational S1 action. And so, oh, I'm getting ahead of myself. So, so what this means is we can have interesting S1 features in the interior of the momentum map. And also, I should mention now that this momentum map image does have a rigid structure to it, similar to the structure that a toric momentum map has. But sort of everything is messed up and bent by the fact that there's a focus-focus point in the middle. So I don't have time to explain this properly, but I'll just say that due to Vunagak in 2007, you can sort of cut out the focus-focus point. That's what this dotted line is supposed to be. And then you can take the rest of the polygon and sort of straighten out its inherent affine structure that makes it want to be a polygon. And so for a semi-toric system, you can end up with this sort of marked polygon invariant. I'll talk more about it in my parallel session if people have questions, because it's extremely interesting, but it takes a little bit of time. Anyway, so the point of this for us when we're thinking about S1 spaces is that fixed points can appear in the interior of the polygon. And so here I've drawn a perfectly valid semi-toric polygon, and you can find the associated S1 space to be exactly the Karshan graph that we had earlier, the one that that couldn't lift to a toric system. And this has been studied by Holak, Sabatini, and Seppi, and also Holak, Sabatini, Seppi, and Symington, sort of a series of papers that are still coming out.
Joey, a 5-minute warning.
Oh, right, thanks. And so, okay, so we're doing blowups on this Karshan space, and let's just continue doing blowups. Okay, so there's rules of how you can do blowups on the Karshan graph, which I'll talk about in my parallel session. I've had to extract all the details to get within 25 minutes. But one of the rules is that an isolated fixed point can always be turned into a Z2 sphere connecting to fixed points. And so here I'm doing some blowups to just to get a new Karshan graph, I guess. And I think, yeah. And it turns out, if I'm careful, I can draw a semi-toric polygon. So this is supposed to be in a 1x1 block, and those lines are each 1/8. So I made sure to get all of the angles right. Let me get rid of the grid. But the point is that this semi-toric system gives me this Karshan graph. That's really all I'm trying to say. That this Karshan graph that I have on the right is a perfectly valid S1 space that can be obtained from this semi-toric polygon. But this will illustrate exactly the remaining issue that I will now solve in 4 minutes, which is I could, if I want to, also do the same thing to this interior fixed point, the one that corresponds to a focus-focus point. And therefore, I'll have 3 different Z2 spheres that all sort of want to be at the same level. And this is sort of where semi-toric systems aren't going far enough. Because if I have 3 different Z2 spheres all at the same level, I can never lift that to a semi-toric system. The only things that can occur in the interior on a semi-toric system are fixed points. Those come from the focus-focus points. So if I again do a blow-up, I get a perfectly valid S1 space that does lift, that does exist on CP2 blown up 6 times, but it can't come from a semi-toric system. And so we're going to generalize this situation further. So this is sort of the new definition. An integral system is called hypersemitoric. Essentially, what we're going to do is take the semi-toric definition, but also allow hyperbolic singularities. So J is going to generate an S1 action, as before. And also, all singularities of F are non-degenerate. So I'm allowing anything non-degenerate. But it turned out that wasn't enough. And I'll also allow singular points, degenerate singular points of what's called parabolic type, which is kind of the nicest type or the most well-understood type of degenerate point. And these systems are not classified, so I can't draw polygons, things like that. But I can tell you about the fibers. So this is sort of a typical picture of a hypersymmetric system momentum map. And it has inside of it this, this triangle. So, so if I'm talking about the fibers, first of all, the corners, edges, and interior points are the same as they were in the semi-toric and in the toric case. But something interesting happens as I get close to this sort of red line. This red line are hyperbolic regular points. And so if I think about a torus approaching that line, the torus kind of pinches off and splits apart. So the hyperbolic singular point is exactly the point where that pinch happens. I have this thing that looks like a figure 8 across a torus. And then it splits into two pieces. And now I can sort of quickly say that, that now the way that this flap sort of behaves is that the fibers separate at that red line. And then other than that, you sort of have two parallel things going on at the same time. On the flap, I have everything happening that would happen at a corner of the momentum map. I have things turning to a circle and things turning to points. While as on the bottom, things sort of go on unchanged. So this is called a flap because you can sort of think of it as glued on along the red line and then hanging off. It's just like a corner of the polygon. And I guess I can just say very briefly, I know I have about 1 minute, that the corners of the flap are where these parabolic points show up. And this is why we want to include degenerate points. So you have all sorts of fibers here. And sort of the point that I can summarize truly in 30 seconds is that the corner on the flap looks just like a corner of the momentum map of the integrable system. And therefore, anything you can do to the corner of the integrable system, you can do to that flap, such as a blowup. And this is going to allow us to do blowups on the interior of the polygon and get those Z2 spheres that we want on the interior of the polygon. So in my last slide here, you can start with a semi-toric system, and there's something you can do called the Hamiltonian-Hopf bifurcation that will turn a focus point into a flap locally. This is all spelled out by Dulin and Pelayo, and many other places. Dulin and Pelayo did it sort of in this context. And then with that flap, you can perform a blowup. And so what I'm showing here is that with a hypersemi-toric system, you can do that blowup that I wanted to do before. And you can take this idea and you can push it quite far. In fact, you can push it all the way. And this is my theorem that will appear tomorrow morning, which is that if you start with any compact four-dimensional S1 space, then you can always find an additional function so that M omega JH is a hypersemi-toric integrable system. And the proof and more information about parabolic points will be in my parallel session. Okay, thank you.
Okay, thank you, Joey. Let's all thank Joey very much for a wonderful presentation. Applause as well as virtual applause. All welcome. Thank you. Okay, so without further ado, let's move on to our next speaker. I just need to find you in the list. Anna, where are you? Here you are. I just need to make you the co-host. Okay, so I've made you a co-host, and now you should be able to share your slides.
I should start sharing now.
Yeah, you can start sharing, yeah. So we'll begin in about a minute. And in the meantime, I just want to, as always, I make kind of these announcements in between the talks just to fill in the awkward silence a bit. So basically, I just want to remind you that the format of these presentations is that each speaker gets 25 minutes, and those 25 for the plenary talk, and those 25 minutes are meant to be kind of uninterrupted. So if you have questions, please feel free to write them in the chat, and come to the discussion session or the parallel talk session and ask them there. Yeah. So okay, well, I think we're okay. I think we can. Yeah, I think we're ready.
Shall I start?
Well, shall I
Okay.
introduce you?
Yeah.
Okay.
So I think Ilya will.
Ilya.
Should introduce the speaker. Okay.
Okay,
Thanks.
I'm happy to introduce our next speaker, Anna Abasheva from Columbia University High School of Economics. Anna will tell us about non-algebraicity for hypercomplex real manifolds.
Thank you for the
Anna, you
introduction.
can start now.
Okay. First of all, I'd like to thank the organizers for giving me the opportunity to talk in this workshop. My topic is non-algebraicity of hypercomplex real manifolds. It lies a little bit far from the mainland of Poisson geometry, but I'll try to make things understandable. I'll start with the very basics about the notion of complex manifolds. In fact, my goal for the plenary talk is to introduce all the required notions needed to state my results. I forgot to say that this talk is based on my joint work with Misha Verbitsky. So I'll start with the very beginnings, with the definition of a complex manifold, which you probably already know. First of all, some linear algebra. If we have a vector space with an almost complex structure, by an almost complex structure, I mean a linear operator whose square is -1, then we have the eigenvalue decomposition of the complexification of this vector space. You see it on the slide. It's the direct sum of V10 plus V01, where V10 is the eigenspace corresponding to the eigenvalue square root of -1, and the other one is the eigenspace corresponding to the eigenvalue minus square root of -1. Then we can move on from the linear algebraic situation to the differential geometric situation and assume that there exists an almost complex structure on a smooth manifold, namely an endomorphism of the tangent bundle whose square is again 0. Then once again, we have the decomposition of the tangent bundle, or more precisely its complexification into the direct sum of two complex bundles, T10 and T01. But on a tangent bundle, we have an additional structure. We have the Lie bracket of two vector fields. So it makes sense to say when the complex structure is integrable. Namely, if we call an almost complex structure integrable, when the sub-bundle T10 is closed under the Lie bracket. What does this condition mean geometrically? There exists a basic result about complex manifolds, Nuremberg theorem, which says that an almost complex structure on a manifold is integrable if and only if the manifold locally looks like an opal ball in Cn. In precise terms, that means that for a point there exists a neighborhood which is biholomorphic to an open ball in Cn, or there exists a chart of holomorphic coordinates near every point. And also, I'd like to add that the integrability condition can be formulated algebraically as the vanishing of a so-called Nienhuis tensor. It's written down on the slide. Of course, you don't need to remember the formula, but you just know that it exists. Complex manifolds are a broad class of manifolds, and we could restrict our attention to Kähler manifolds. What a Kähler manifold is. Once again, we start with a little bit of linear algebra. Let V be a real vector space with an almost complex structure R. We can endow it with an Hermitian metric. By an Hermitian metric, I mean a Euclidean metric such that the complex structure is orthogonal with respect to this metric. The orthogonality condition is written down on the slide. It's G of IV, IU is equal to G of V. Given this data, we can construct an arbiter tensor. It's the two-form omega. Omega is obtained from G by adding I to the first argument. A simple linear algebraic argument shows that it is a skew-symmetric to form. The same, of course, can be done on a complex manifold. So first, we endow complex manifold with an Hermitian metric. When from this Hermitian metric, we get a two form. And next, we could check if this two form is closed. And if it is, then we call a complex Hermitian manifold scalar. Most complex manifolds you can think of are scalar. For example, a projective space scalar of any dimension, and all smooth projective varieties are scalar, namely all subvarieties of the projective space. Opposite is, of course, non-true. Not all scalar manifolds are projective, but all projective manifolds are scalar. A counterexample is given by a complex torus. By a complex torus, I mean a quotient of Cn by a lattice. It is well known that some complex tori are algebraic and some complex tori are not. And in fact, almost all complex tori are non-algebraic. And an instance of the first example, where I said that every submanifold of CPN is scalar. A third example, a complex submanifold of a scalar manifold is scalar. I introduce scalar manifolds here just to say that the manifolds we are going to work with are not scalar. That's why they often enjoy really weird properties which don't look, which just can't be obtained by common sense. Namely, I'm going to work with nil manifolds. So, of course, I need to introduce what a nil manifold is. We start with a nilpotent Lie algebra. What is a nilpotent Lie algebra? Okay, for every Lie algebra, we can define its lower central series as follows. First, we define G1 to be the commutant of this Lie algebra. Then the definition goes inductively. We define Gi to be the commutator of G with Gi minus 1, and so on and so on. And if this lower central series converges to 0, then the Lie algebra is called nilpotent. Or in other words, it means that for some finite number k, Gk is 0, it vanishes. This was a definition of a nilpotent Lie algebra, and exactly in the same way, one can give a definition of a nilpotent Lie group. Nilpotent Lie groups are non-compact, but there is always a way to make them compact. By a theorem of Maltsev, there always exists a co-compact lattice in an important Lie group, namely a discrete subgroup of G, such that the quotient of G by this subgroup is compact. Then the quotient of G by gamma is called a nil manifold. One should be really careful here about right and left. Here we take the quotient by the left action of gamma. So on the quotient, the group G acts on the right. So on G there exists a left action and a right action, and on the quotient there exists just a right action. Next, we are going to introduce complex structures on nil manifolds. So first, let's talk about what are complex structures on Lie groups. First of all, as you probably know, every vector in a Lie algebra defines a left invariant vector field on the whole Lie group G. And the map sending a vector in the Lie algebra to the corresponding left invariant vector field is an isomorphism of Lie algebra. Exactly in the same way, if one has an almost complex structure on G, on the Lie algebra G, then one can form from it a left invariant almost complex structure on the whole Lie group G. And I state on the slide a very important fact that the almost complex structure on the Lie group is, the almost complex structure on the Lie group is integrable if and only if G10 is a Lie subalgebra of the complexification of G. G10 is defined as, in my first slide, as the eigenspace of the complex structure. Why is it so? Well, we have to check the vanishing of some tensor. So we have to check, in fact, that it vanishes on all vector fields, but left invariant vector fields on the Lie group generate the spaces move of vector fields. They generate this space over the smooth function. So we have to check the integrability condition just for them, and the claim follows. What is important here? That a left invariant complex structure on G makes G into a complex manifold by Nylander-Nirbach theorem. But that doesn't mean that G becomes a complex Lie group. There exist example of left invariant complex structures on Lie groups, which are not right invariant. But a complex structure on a complex Lie group, of course, it has to be both left and right invariant. In linear algebraic terms, the integrability of the complex structure was expressed as a condition that G10 is a subalgebra of the complexification of G. But if G is a complex Lie group, then G10 is an ideal of the complexification of G, and of course this condition is stronger. So, okay, let's start with a nilpotent Lie group with a left invariant complex structure, just left invariant, not necessarily right invariant. Then we can find again a co-compact lattice and take a quotient, and this quotient inherits a complex structure. However, as I already said, the group Gx on this quotient on the right and this right action need not preserve the complex structure. I'll give an example of this phenomenon in the parallel talk, but now let's discuss a simpler example when the complex structure is both left and right invariant. Here is a basic example of a nilpotent Lie group. The complex Heisenberg group here, it is of dimension 3. It is a group of upper triangular matrices with ones on the diagonal, and their coefficients lie in C. How we construct a lattice in this group? We take a quadratic lattice in C. By a quadratic lattice, I mean Z of square root of -1. And we consider the subgroup of matrices whose coefficients lie in this lattice, in this quadratic lattice. Then we take the quotient, and this quotient is called an Iwasawa manifold. What is interesting about Iwasawa manifold? That it is in particular non-scalar. And actually all complex nil manifolds are non-scalar. So the objects I'm going to work with, complex nil manifolds, or in fact hypercomplex nil manifolds, are all non-scalar. But what was the topic of my talk? It was not about complex nil manifolds, it was about hypercomplex nil manifolds. I have to say a little bit about what a hypercomplex manifold is. Let's start with a little bit of notation. By this fat H, I always denote the quaternion algebra, namely a 4-dimensional algebra over the real numbers, which is generated by 3 complex structures IJK with quaternionic relations, which you probably know. They're written down on the slide. IG equals to K, and all 3 complex structures anti-commute. There is a simple algebraic fact that it is trivial to check, that a quaternion, an element of the algebra of quaternions, is a complex structure. That is to say that its square is -1 if and only if it is a linear combination of complex structures I, J, K with coefficients, say, x, y, z, and x squared plus y squared plus z squared equals to 1. Therefore, there exists a whole two-sphere of complex structures in the Lie algebra of quaternions. Okay, let's move on to the geometry. Recall a smooth manifold hypercomplex if there exists an action of H on its tangent pattern. So there exist three complex structures on it which anticommute. Recall this manifold hypercomplex if every complex structure induced from the quaternions is integrable. In fact, it's enough to check integrability not for the whole sphere of the complex structures, but just for two of them, for example, just for I and G. So this is not a really strong condition. Okay. In the same way as we gave a definition of a complex Lie manifold, we can give the definition of a hypercomplex Lie manifold. But here we start with an important Lie group with a left invariant hypercomplex structure. Then we find an eco-compact lattice in it, take the quotient, and the quotient is what is called a hypercomplex Lie manifold. Okay, so I'm almost ready to state the main theorems of my work. First of all, let me introduce a little bit of notation. So here is this strange symbol on the slide, for all L in H. It will always stand for the phrase for all but a countable number of complex structures L in H. So we have a sphere of complex structures, and this symbol means that we can raise a countable number of points, and what is left is a generic complex structure. So I just will say a generic complex structure for short, but that's what it precisely means. My work is concerned with the behavior of hypercomplex manifold when we change the complex structure. So if X is a hypercomplex manifold and L is some complex structure in the quaternions, we denote by XL the manifold which is the same as X as a real manifold and whose complex structure is L. So we consider it as a complex manifold with a complex structure L. So the first theorem goes as follows. Let X be a hypercomplex Lie manifold. When we claim that for a generic complex structure L in quaternions, the complex manifold XL doesn't admit a non-trivial meromorphic map onto a Kähler manifold. What do I mean by a meromorphic map? So a holomorphic map is the map which is locally given by a collection of holomorphic functions. A meromorphic map is a map which is locally given by a collection of meromorphic functions. That is to say, we allow denominators. So it is a fair holomorphic map on a dense open subset of X. In particular, of course, X doesn't admit non-trivial holomorphic map onto a Kähler manifold. So it is not only non-Kähler, but even stronger, it doesn't admit maps onto Kähler manifolds, except, of course, for a point. The second theorem is about subvarieties of a complex Lie manifold for a generic complex structure. Unfortunately, in the statement of this theorem, we have to impose another condition on X, namely an existence of an HKT structure. I'm not going to say now what an HKT structure is, you should just understand that it is some condition which arose first in string theory and found its use in mathematics, and it's just some natural condition to impose. Okay, so if X is a hypercomplex nil manifold admitting an HKT structure, then for a generic complex structure induced from sequatinous, every complex subvariety of XL is hypercomplex. In particular, every complex subvariety is even dimensional. What does that mean? For example, it means that
5-minute warning for you.
Okay, thank you. In particular, this means that there are no curves in this variety, and this is really different from what we have in the algebraic form. In any algebraic variety, every 2 points can be connected by a curve. So there is a bunch of curves on an algebraic variety, and here we have just none. And the same thing for devices. There always exists a non-trivial divisor on an algebraic variety, and in fact, a bunch of divisors, and here we have none, because all the subvarieties have even dimension. That's pretty weird. So my time is going to finish soon, so I'll just say what I'm going to talk about in the parallel session. First, I promised you an example of a Lie group with a left invariant complex structure, which is not right invariant. And in fact, I'm going to spend some time on examples. I'm going to introduce you an example of the Kadir surface. This is more or less the same as the example of a Lie group with a left invariant complex structure, which is not right invariant. Then, of course, I should say a little bit about how to construct hypercomplex nil manifolds. That's an interesting construction called the Dublin construction. And then we slowly move on to the proof of this theorem. I believe that I'll be able to give an overview of the proof of the first theorem. I'm not so hopeful about the second theorem, but I'll say at least a couple words about it, and the proof is written down on the slide, so you can read it anytime. So I think I'll finish now. Thanks for your attention.
Okay, thank you very much, Anna. Let's all thank Anna very much for her wonderful lecture.
Thank you.
Right. Okay, so we're quite ahead of schedule, which is unusual. But okay, so let's see, where is our next speaker? Jacob, there you are, I see you. So I'm just going to make you a co-host. Okay, so now you should be able to share your screen. Okay, so in the meantime, we'll start in a few minutes. So let me just say 2 things. So first of all, as always, we encourage everyone to switch your videos on if you can. That always helps not only the speaker to feel that they are actually speaking to other humans and not into a void, but actually other members in the audience as well. You kind of, when you see other faces, you feel like you're part of this, some kind of community movement or whatever. And for you, each individual one of you personally, it's also a good idea, because the more people see you, the more they remember you. So yes, if you can, please do keep your cameras on. That would be great. Oh yes, excellent. So many more videos on. That's awesome, fantastic, love it. Okay, so the other thing that I wanted to say is, I'm sure you've already read it from the hundreds of announcement emails that we've sent in the last few weeks. There is also going to be an award for best contribution for our speakers. There's 4 awards in total. 2 will go to PhD student speakers and 2 will go to postdoc student speakers. And it comes with a prize worth £150. So that's good. But of course, hopefully just getting an award itself is going to be a massive boost to your kind of enthusiasm to really present and do your best and get the best, most memorable experience out of Junior Global Poisson. We really hope, we really kind of really want to kind of think of Junior Global Poisson as a place for everyone to grow, to really if this leaves some kind of lasting, even tiny bit of memory in your academic or non-academic career progression, that would be a dream. That would be fantastic. So so this is just our small way to go in that direction. So so I want to say a couple of words about the award. So it'll be judged. There's 3 award panel members. There's Anastasia Matveyeva, Francis Bischoff, and myself. And we'll be judging the plenary talks only, and we'll be judging them based on presentation skills only. So this is going to be no reflection at all on how monumental your mathematical achievement is. So we definitely don't want to pretend that we is qualified enough to make that sort of judgment. But something we do want to encourage as part of Junior Global Poisson is the importance of being part of the community and presenting your research. And so those are the kind of skills that we want to encourage people to improve. And so that's what the awards will go for. So the 3 keywords are clarity, engagement, and delivery. So definitions of those words are very fluid, and everyone should probably have their own definition of that. Yeah, anyway. Yeah, well, one thing I can say for sure is that having heard just 2 talks so far, I can already tell that we've set ourselves up for quite a challenge. It's going to be quite difficult to judge. Yeah. Okay. Yeah. So Nastya, Leonard, Ilya, do you have anything to add in terms of announcements for the conference so far?
You're trying to fill the last 3 minutes?
Yeah. Yes, exactly. That's exactly what I'm trying to do. I don't want to start early. I think we should start on the hour. I mean, on the. That's right. Yeah, on the hour. So
okay,
we have 2
can
minutes.
Announce Jeffrey's part today's.
Oh yes. Oh yes, that's right. So one thing that is very cool also today is there's going to be a professional development session. It's going to be right after the parallel sessions. It will have maybe something like a 15-minute screen-free break for everyone to kind of rest your eyes, and then we'll come back to the same room. We'll do this in this Zoom meeting room, and Jeffrey Scott is going to give a presentation, basically about opportunities outside of academia. So Jeffrey Scott is a former mathematician himself. He was a postdoc in Toronto, which is where him and I met. And then for about 3 years, he's been working at Google as a machine learning guru. He'll say the correct thing. So he had a very positive experience with this, and he very kindly agreed to share the challenges, the pitfalls, and the advantages. So do tune in. I think it's going to be a wonderful session. Okay, so I think we could start. By my clock, it's okay. Yeah. Okay, so let me introduce the speaker. So we're very happy to have Jacob Kryczka from La Rima which is at the University of Angers in France. And he's going to talk to us about local gauge field theory from the perspective of nonlinear PDE geometry. Okay, take it away, Jacob.
Perfect. Thank you for the introduction. Just want to make sure everyone can hear me all right. Yep. All right. So first, I'd like to thank the organizers for giving me the opportunity to speak at this conference, and also for just the level of work that went into getting it all ready and how professional everything is. It's quite amazing. So clearly, based on my talk title, I'm going to be discussing local gauge field theory from a very specific perspective, which is based on the geometric theory of PDEs. So just some general structure for how I think I'm going to proceed today in both of my talks. I want to give a lot of motivation as well as in general, just some philosophy behind the constructions we'll see. And I want to use these kind of tools that I'll develop to say something about PDE geometry in a very generalized sense. And this is technically quite complicated, so we'll develop some results by applying it to gauge field theory. Okay, so the introduction. I just want to say about myself quickly. I am currently in my final lap of my PhD at Arima. My thesis advisors were, or maybe I should say, are Volodya Rubtsov and Alexander Vinogradov. And my research interests are, of course, broadly speaking, related to the geometric theory of PDEs. So I think the best way to start is to mention a preliminary analogy that was used in the help to motivate the geometric theory of PDEs as we know it today. And this comes from algebraic geometry, wherein, as you all probably know, we study systems of polynomial equations, and you can study such an algebraic object in terms of a geometric object, and this is the algebraic variety. While on the PDE side of things, similar considerations lead to a geometric object as well, which is called by Vinogradov a diffiety, or which is short for differential variety. And actually, this kind of analogy was made precise in a different manner by Frédéric Pogam in around 2014, 2011, using a functor of points approach to studying generalized spaces of equations. So here I've compiled a little chart that shows exactly this relationship. It's quite precise, actually. It demonstrates that while in algebraic geometry, we study commutative algebra as well, on the PDE side of things, by studying a particular kind of algebra, namely a D-algebra, or an algebra over the ring of differential operators on a manifold, we can actually proceed very analogously. So today, the main goal is to use this kind of philosophy and proceed further by essentially wanting to consider systems of PDEs in the presence of symmetries. And this is a very loose term, but it will be made precise as we go along today. So just again, to reiterate the structure, this plenary talk is mainly to give motivation. I'm going to motivate some functorial techniques, and I want to end up stating a theorem that characterizes the derived covariant phase space in terms of the Euler-Lagrange critical locus. In the parallel talks, I'm going to provide a bit more background and some details and maybe some examples, depending on what the interests and the needs are of the people who attend. So I've created just a little roadmap here of relating some areas to some buzzwords that people might be familiar with. I don't want to say anything about this now, but I attach it here just for your general education, and if you want to take a look at it to see if it relates to something you may know. And I want to quickly mention just some related areas. So the formal theory of PDEs is one of the underlying tools used in the geometric theory of PDEs, as we'll describe today. But also this is applied to the formal theory of PDEs and the calculus of variations. So I attach here a link to Ezra Getzler's talk that was recently given as part of the Global Poisson webinar series. You can click this and follow it. So I also want to mention there's an approach related to chiral algebras, and also these kind of all of these ideas coalesce and fit naturally into a more homotopical mindset of derived geometry, which have had amazing applications to symplectic geometry. For instance, the AKS-Z formalism appears as a fully extended topological field theory, and this was also discussed in a previous Poisson webinar series. So, of course, this is a Poisson conference, so I want to say a few things about Poisson geometry and try to relate it to the broader goal. So in ordinary finite dimensional Hamiltonian formalism of classical mechanics, it's, as we all know, we have some kind of smooth variety and a Hamiltonian function, which generally represents an energy. And then we have a Poisson bracket, and we can study the time evolution of the system in terms of typically an ODE. Once we go to integrable systems or something like field theory, typically this is infinite dimensional, and broadly speaking, these can be described by a class of PDEs that are often called evolutionary. So here I write them down for simplicity for two, or just depending on one spatial variable. And one can make sense of a notion of when these types of systems admit a Hamiltonian formulation as well. And typically what you need for this is some kind of matrix differential operator and some density, which is the infinite dimensional analog of a Hamiltonian function, such that you can render your equation of motion in a particular way. So analogously to the Poisson bracket in the finite dimensional case, under certain circumstances, we can have that this matrix differential operator determines what's called a local Poisson bracket. So on what space is this defined? Well, on one hand, you can describe them in terms of a space of differential polynomials with some commuting derivations, but also on a space of local functionals. And this is typically the space, universal space where integration by parts holds. So, and the local Poisson bracket then appears as a Lie algebra structure on this space. There's also a way that you can view local Poisson brackets constructed in this way in terms of a more geometric interpretation, and this is by viewing them as functions on jet bundles. So in particular, we can regard functions as I mentioned above, as coordinates on a type of manifold called the infinite jet space. So in the framework of Vinogradov's school, PDEs are studied as submanifolds in a certain finite dimensional jet space, representing the order of the system. And the formal theory of PDEs suggests that we take the infinite prolongation or the differential consequences. And this is endowed with a canonical involutive distribution called the Cartan distribution. Pairs of these form are called diffeities. And in general, one can develop a theory of calculus on diffeities. And this is discussed in terms of natural cohomology theory associated to these objects. And I refer you to another Poisson global webinar series by Luca Vitaliano that discusses an aspect of this approach as well. So on the other hand, this can be viewed in an algebraic way that we'll be adopting today, where one might identify a differential algebra with an additional algebraic structure, which is a D algebra. So this is a module over the ring of differential operators, equipped with some commutative structure. And the prototype example for us are the smooth function algebras on infinite jet bundles. One of the insights of Beilinson and Drinfeld's approach to chiral algebras is that the geometry of such operations appear and are described in terms of spaces of local operations, which are given in terms of this kind of expressions here that I'll mention more in the parallel talk. Essentially, local Poisson brackets, as we've seen, then appear as suitable binary operations in this way. Sometimes they're called Poisson as a compounded word for compound local Poisson. So in fact, one should, it's known that due to Francis and Gates-Scory's insights that one should essentially be working with these operations over a larger space of more homotopical flavor, which is the Ron space. And this is quickly very involved, so with using infinity categories and whatnot. So today I'll try to give the gist of everything in the context of the local operations in the sense of valence and Drinfeld. Okay, so without further ado, we should get going on how we can go about studying gauge field theories using this language. So of course, when you want to study physics, typically we have some bundle whose sections are the space of fields, and one writes down an action functional, which depends on these fields, their derivatives, and things like this. So in physics, we care about making measurements, and typically a physicist might write down some expressions in terms of a partition function or path integrals like this. But proceeding in this way, you need to be careful. For instance, in supersymmetric theories, where we need a good notion of integration so we need to use Berezinians and things like this on supermanifolds. So for today, we want to be working in a sufficiently general language where we can treat field theory in a sort of universal sense. So in this direction, we follow Frederic Pogam's convention of calling a space of affine building blocks on which we'll build a geometry called a space of Legos. Typically, these are just the opposite category of a commutative algebra objects associated to a closed symmetric monoidal category. Then we can pose a general definition of what's a Lagrangian variational problem related to this closed category C. And this is a pair of Legos and a morphism with some additional assumptions that, for instance, it should be a bundle or a morphism of locally ring spaces. And we want to pick a subspace of the space of sections and define some kind of some functions on this space, typically representing the action functional. So here and throughout the talks today, I will use an underline on a given space to emphasize that I'm using the viewing it as a functor of points. So if you don't know what this is, that's all right. I'll be using this word a lot in the plenary talk, but I'll make it more precise if you need in the parallel session. Using the functor of points is important. For instance, it gives us a way to talk about the parameterized functional geometry on spaces of trajectories. And this is important in physics. So typically our space of interest is actually the critical locus or the space of classical trajectories. And these are all the histories that satisfied this relation here, which defines the minima of the functional. Okay. So of course, this is what the principle of least action that I'm sure everyone is familiar with is. It gives us a way of passing from the critical space, so all fields that are minimas for the functional, these are the same things as those fields satisfying a particular solution, a system of PDEs, namely the Euler-Lagrange equations. So following the formal theory and the geometric theory of PDEs, we want to study this PDE side of things rather than the critical locus side, although they are essentially equivalent by this well-known principle. But we want to study this system together with its differential consequences. Of course, also in physics, there's usually some kind of symmetry group at play. And so we want to study the gauge invariant observables. And what this amounts to, roughly speaking, is passing to a reduced space of classical trajectories. These spaces are typically infinite dimensional, as I'll mention. But modulo those issues, we typically want to view this reduced space as a Hamiltonian or Poisson reduction of the classical trajectories. Okay, so just some to summarize so far, well, we want to study quotient spaces like fields modulo gauge symmetries and functionals on them. Typically, both fields and the space of gauge symmetries are often infinite dimensional. The action of this gauge group on the space of fields is not a free action, so this quotient is typically quite ill-behaved. And moreover, the space of critical points is well known to be a non-transversal intersection given by a fiber product here, or homotopy pullback. And then typically, we can fix these issues by viewing all spaces at play as some kind of generalized space, as sheaves or something like this. We can view fields modulo the gauge symmetries as a higher categorical object that is allowed to possess automorphisms that are non-trivial. These go by the name stacks. And we can remedy the non-transversality issues of the critical locus by viewing it as a homotopy fiber product or a derived intersection. So this so-called derived critical locus that one arrives at by considering this has been studied by various people. It's well known that in general, it is described in terms of a mathematical gadget called a derived stack. And it is canonically -1 shifted symplectic. So this means it just carries a symplectic form with a particular cohomological degree. Typically, derived stacks in the geometric sense are quite difficult to work with. So you could work in specific cases at the level of global functions. So this would amount to defining a homotopy pushout. And following these considerations, in cases of interest, one can see that the derived critical locus appears as a -1 shifted cotangent bundle. This is one explanation for the shift, but for the shifted symplectic structure. But another one comes from a very powerful and elegant theorem due to the PTVV crew describing Lagrangian intersections in a shifted symplectic space. So now we want to pass to our PDE perspective. So very broadly speaking, we are going to study the systems of PDEs in the presence of symmetries, but we want to be able to apply them to cases where we can study evolutionary PDEs, as I mentioned earlier, those that render themselves also in Hamiltonian form, and theory of local Poisson structures. But also we want to apply them to Euler-Lagrange systems as well. And this is what our focus will be on today. But as we've seen, the derived critical locus is some higher mathematical gadget that I call the derived stack. If you don't know anything about this, that's totally fine. It's just some placeholder name for homotopy theoretic tools. So we expect that on the PDE side of things, that such a PDE should also be of this kind of higher mathematical nature. So in order to discuss this, let's just mention quickly how to view equations as generalized types of spaces using the functor of points approach. So in a given category of Legos, typically it has a few drawbacks as well. There's not enough limits or co-limits. This is one of the reasons for why the critical locus was ill-defined. So we have lack of solution spaces, or I mean fiber products, but also the quotient itself of the field's modulo gauge symmetries might not exist either. So to remedy such things, we will view our Legos by their functor of points. So written here, it's defined by mapping, probing it or testing affine spaces into your geometric objects. So we'll proceed by calling, generically speaking, a space modeled on a site Legos. So by site, I mean a category of Legos with some growth and dig topology. It doesn't matter what this is, it just gives a way for studying local to global properties. And that's reflected in the mathematical term of a sheaf. So a typical example that is a very important and guiding example, again, is the system of polynomial equations. I don't want to mention this because it might be familiar to everyone, but essentially speaking, now we want to ask, do these considerations hold also for nonlinear PDEs? The way to see this quite easily is to understand the linear setting. So this is the theory of D modules, where typically one wants to study the solution space as a kernel. It's very well known that the functor of points is the appropriate language to study such spaces. However, in general, a given system of PDEs may not be homogeneous. And in fact, it could be overdetermined. So there might be algebraic compatibility relations between solutions and obstructions to solutions. It's very well known that these kind of instances are described using the language of derived and triangulated categories. And what you arrive at is the so-called derived solution functors. It's important to note that these are formulated in terms of a kind of duality operation called the derived dual D module. But also this formalism is a very powerful and convenient one for many reasons. In particular, there's the six functor formalism. So we have push forward, pull back, and all that good stuff. But also we have a very nice notion of duality, which is the Verdier duality. So what can we say now about the nonlinear setting? Well, for one, morphisms between two D algebras in the setting that we want to be taking does not carry in any natural way a vector space structure, but this is fine by using set valued sheaves instead. So for nonlinear PDEs, one can define the associated solution functor from the functor of points approach as what are called D spaces or affine D schemes. The prototypes, of course, for us are going to be the jet schemes. And in general, when it need not be affine, we just call these algebraic D spaces. So suitable functors satisfying a good notion of sheaf condition with respect to some topology on the site on the category of commutative D algebras. So when our D space is not, when it is affine, so it's in particular cut out by a D ideal, so a system of PDEs in a D algebra, we can associate also another functor of points called the non-local solution space. And this is no longer a sheaf on the commutative algebra site, D algebra site, but on Legos. So using
Jacob,
what, yes?
Jacob, a 5-minute warning.
Okay, thanks. So using what physicists might call trying to make precise what they might call a gauge theory, a very loose term thrown around, one can say that Lagrangian variational problem, as I defined it, is called a gauge theory or D gauge theory if it has nice histories. So what does this mean? It means that the space of classical trajectories identifies with the non-local solution space. Here I write it in terms of the ideal cut out by the Euler-Lagrange ideal that I'll mention in my parallel talk. But for the remainder of this plenary session, I want to move on to state my result, which is to clarify, once we pass to the derived critical locus, what happens on the PDE side of things. So this brings us to what we'll see in the parallel talk, is that we will study a nonlinear PDEs as a class of homotopical spaces, so suitable homotopy classes of functors. And they're represented by very special kinds of homotopy algebras. For one, they're differentially structured. I won't say any more about that right now, but also they become suitably finite dimensional in a very particular case as well, which is important. Also, they possess a nice subclass of objects that admit finiteness conditions, which are necessary to impose when studying spaces of Noether identities and gauge field theories. And explicitly, these correspond to various infinity categories of D algebras. So they could be regular, holonomic, and things like this. So just throw in adjectives from those areas of mathematics that are of particular importance. And another important point is that they admit extensions to what are called factorization algebras or factorization versions of these homotopical sheaves. So I write here commutative D algebras as L, which this is a homotopy localization of some other category. And this is actually one that has been endowed with another homotopy structure, which goes by the name of a model structure. This was established by a group of people, Gennaro Debrino, Damian Pistallo, and Norbert Poisson. And this is essentially the starting point for where you can proceed down this road of homotopy theory of PDEs. So the main theorem that I'd like to state that I will spend the parallel talk proving is that if we take a D gauge field theory as I've so defined them, we may canonically associate D pre-stack, whatever this fancy term is. If you don't understand what stacks are, that's fine. Just so this represents the solution space of the field theory, and we can define its sort of homotopical enhancement, which is this R sol. So this is the derived D pre-stack. In order to view this as a homotopy, a functor between homotopy categories in this way, a bit of work needs to be done. And this will be the main content of the parallel talk. In this setting also, what's very nice is we have a nice duality operation as well. That is sort of the non-linear version for the Verdier duality, which is what we call local Verdier duality. And actually, this can be used to define the spaces of interest for derived geometers, like the cotangent complex and tangent complexes, but in the derived D setting. And we also need to use these kind of dualities to impose finiteness conditions when studying field theories, but in the homotopical mindset. So my theorem is that I'll mention is that which basically explains or just characterizes where this derived D pre-stack lives, which category it lives in. So if A is the Euler, or A with the subscript EL is the Euler-Lagrange D algebra associated to a field theory or a gauge field theory, then this derived solution space, according to this procedure above, is what the physicists would call the derived covariant phase space. And this is canonically a symplectic D stack as an object of some magical looking category here. Roughly speaking, this is a homotopic category of some localization of a category of functors in a very homotopical way with respect to a class of topology that should be specified. So the last things I want to mention with this, I guess, maybe 30 seconds or a minute I have left is that these kind of objects in the D setting were first described by Frédéric Pogam, where he mentions how the BV formalism in gauge field theory can produce, it produces basically an odd local Poisson or Poisson differential graded dx algebra over the algebra of functions on the jet space, and correspondingly a derived D space that I've written here. And roughly speaking, this should be interpreted as the homotopical Poisson reduction of the derived critical locus by defoliation induced by gauge symmetries. In order to do this, and one needs to impose finite conditions, finiteness conditions in the BV algebra here, and I'll describe some more of this in the parallel talk. So I guess just one last final remark is that we can go even more nonlinear, I guess, if by studying so-called derived D spaces, which are, I guess, a more stacky even version than the nonlinear theory based on D algebras by a kind of homotopy multijet construction. And but to do this, one needs to use the technologies of de Rham spaces in derived algebraic geometry or smooth or even analytic geometry. So if you're interested in this, you can talk to me. But for now, I think I'll just see you all or anyone who's interested in the parallel session. Thank you very much.
All right. Thank you very, very much, Jacob. Let's all give a round of applause to Jacob for an excellent lecture. All right, excellent. So without further ado, let's move on to the next speaker. Luis, where are you? Oh, there you are.
Fine.
Excellent. So I think I've already made you a co-host.
Okay, let me see.
Have I? Yeah, you should be able to share now. Yeah. Okay, so in the meantime, I just want to say a couple of words about the parallel sessions, just the procedure. So what will happen is after Luis's talk, there will be 1 hour of parallel sessions, and this will be in the same Zoom meeting room. So you don't have to switch to a different meeting room. So this is kind of slightly different to what we had last time, if you remember. This time, everything remains in this meeting room. What's going to happen is we'll open 4 breakout rooms named after each speaker. And as participants, you're able to you'll be able to jump from one breakout room to another. So you can just choose whichever one you wish to go to. We'll also open a few extra kind of overflow breakout rooms in case you want to kind of go in seclusion and discuss something with other people. But basically, just stay in this room. Yeah, that's the message. Okay, we have another minute before Luis should start. Let's just wait. Not enough time to go and make coffee. That's unfortunate. Maybe these breaks should be longer. Okay, I guess we can begin. So, Leonard, would you like to introduce the speaker?
Yes, let me first say that I'm very delighted to see all of you come together here to talk about Poisson geometry. It's kind of a light at the end of the tunnel, and to see that there's so many other people on this planet that have the same interest in mathematics. So it's personally very good feeling to see you all come together here, and it makes it worth the time spent organizing this. But now, without further ado, just to stick to the schedule, I'm happy to introduce Luis Alejandro Barbosa Torres from the University of Sao Paulo, and he will talk about equivariant cohomology models for differentiable stacks. Please go ahead.
Thank you so much. First, I want to thank you all for giving us this space and to share our research. Today, we're going to talk about my PhD project when I was in the University of Leicester, and as makes part of a joint work with Frank Neumann as well. So today I'm going to talk equivariant cohomology for differentiable stacks, and my idea is do an overview in all these concepts. So first of all, we are going to check what is the classical problem. So the idea is you have a Lie group acting on a smooth manifold M, and we want to get a good notion of cohomology for the quotient space M over G. But this space is not always a smooth manifold. So sometimes it's not possible to do it. So we are going to try to get some models that allow us to do that. So our first model was done by Borel, and the idea behind that is trying to find a contractible space E with a free action on it, and try to consider an action that is going to be induced in the Cartesian product between E and M, and this action is going to be a free action. So if we have that, we are going to be able to consider this quotient space. As we are asking that this space is contractible, the cohomology of this space is going to be isomorphic to the cohomology of the space of the quotient space M over G, and in that way, this space is a good candidate for the definition of equivariant cohomology, and actually that's the case. That's the definition of equivariant cohomology. So the idea is try to find a space E that allow us to do all these things. So there are several models to do it, but we are gonna focus in one related to the transformation groupoid. The transformation groupoid is there exists when you have a Lie group acting on a smooth manifold X, and you are going to consider the arrows in that Lie groupoid just like this, and the points just as the manifold, where the source and the target map is the projection and the action on it. Okay. One thing about groupoids is that you can associate a simplicial smooth manifold. So how can you do that? Well, if you have here the arrows, you can consider the double composition of arrows, the triple composition, four composition of arrows in here, and so on. Okay, this is gonna give you a smooth simplicial smooth manifold, and in our case, but we are gonna get something like this, and this simplicial smooth manifold is gonna be called nerf of the Lie groupoid, and in here you're gonna see the points, the arrows, the two compositions, the triple composition, and so on. And in our case, you can see that these arrows, these triple compositions, double composition, actually are isomorphic to these smooth manifolds, where G squared here is the Cartesian product of G by itself times the smooth manifold X. So in here, you're gonna have G3 times X and so on. When you consider as well the arrows, in here, you're gonna get the source and the target, but in here, you're going to consider the possible ways that you are going to have from a composition of 2 arrows to get just 1. So you can just drop the first one, drop the second one, or just make the composition of both of them, and you're going to get just 1 arrow here. When you do all these computations, what you're going to get is that the faces of this nerve is going to look like this. So the 0 face is going to be just taking an element in here and just drop the first element. If the phase is between 0 and n, you are going to just using the multiplication of the group. And for the last phase, you are going to just using the action next. Okay, so this is an important and a key example for us for this talk. Okay, so we have a groupoid. We are having a simplicial smooth manifold. And for those simplicial smooth manifold, we can associate a topological space. The way to use it is using the fat, to do it is using the fat geometric realization for a simplicial smooth manifold. So the idea is try to consider this cushion space that is going to be using the usual topological simplicial sets. And we are going to use its faces there to glue all together in this way. When we have that, the good thing about the transformation groupoid is that actually the nerve of the the fat geometric realization of the nerve of the transformation groupoid is going to be give us the space that we are looking for. Okay, that's the idea. Okay, but there are more models to get the notion of equivariant cohomology. In this case, the Cartan model, it was try to use the differential information on the smooth manifold to try to get the notion of equivariant cohomology. So in our case, we are going to just use a compactly group on the smooth manifold M, and we are going to see that the equivariant forms are defined as polynomial maps between the Lie algebra of D and the round complex of differential forms. They are going to be equivariant because in here you are going to have the adjoint action, and in here you have the action given by the pullback when you fix the action in a point of G. Okay, so in this way it's going to be equivariant, but this actually can be seen as this space of invariant forms, where this part here are going to tell us about the polynomial form in the equivariant, the equivariant form, and in here you're going to get the differential form with this gradation that is twice the polynomial plus the degree of the form. And the differential is going to be given by the stereo derivative minus the contraction in the fundamental vector field. Okay, this differential we are going to call the Cartan differential. The good thing, that's a theorem given by Cartan, is that these complex are going to compute the same cohomology as the Borel model. Okay, so this is a good thing. So now I'm going to try to explain you how I see stacks in my research. So there are several ways to see how it works a stack. So in my case, I'm going to consider a stack as a two shifts over groupoids. That means that you have pseudo functor. That means you send identities to identities, but the compositions of maps here are going to be just going to up to isomorphism compositions of maps. That's what it means pseudo functoring here. And you can glue objects and you can glue morphisms in here. Okay, we have this property for the stacks. Some examples for this is try to extend the notion of functor points for a smooth manifold X. So one way to associate a stack for a smooth manifold is consider all the mass that goes to X and consider this as a group point with identity maps, okay? As well, a really important example is the classifying stack for a Lie group that is gonna take a smooth manifold M and is gonna associate the category of principal G bundles over M. This category is already a groupoid because all the morphisms between principal G bundles are gonna be isomorphisms. And you can glue all these elements together because you have all the conditions in the cocycle conditions in here in principal G bundles. So it's possible to see this as a stack. Then combining in some way these two examples, we are gonna have the next one. This is when you have a Lie group acting on a smooth manifold X, and we are gonna call the quotient stack for the smooth manifold X. And what it's gonna do, it's gonna take a smooth manifold Y and it's gonna assign a Lie groupoid whose elements are pairs, where the first one is a principal, this is principal G bundle, and F is a equivariant morphisms. The isomorphisms of this groupoid is gonna be given by morphisms of principal G bundles. That means there are isomorphisms that are well behaved with respect to this F, okay? This construction is quite classical in this context of the stack, so please keep this in mind. Okay, so we have the notion stack over the category of diff. And now we can go to our principal principal definition in our case, that's the differential stack. So a differential stack is a stack over diff such that you are gonna ask a little bit more. So there is gonna exist a smooth manifold X and an morphisms of a stack. So check here that is X, but it's actually the stack associated to that smooth manifold. And we are gonna ask two properties. One is that for any morphisms of a stack between Y and M, where Y is a smooth manifold, you can do in this category pullbacks. So this pullback in here is gonna be isomorphic to a smooth manifold. And second, you are gonna ask that the morphism that comes from that pullback is gonna be an submersion or has localization, okay? This map is gonna be it's gonna be called an atlas of M, okay? And why is this important? Well, using an analog of absorption groupoid, you can associate for a differential stack a Lie groupoid in this way. Okay, so this is going to be the Lie groupoid associated to the differential stack. Okay, so so from differential stack we can go to the Lie groupoids, and these two categories have really strong relation. So we are gonna make a small review of that. For example, if you take any Lie group, you can associate a differential stack. The way to do it is try to use a notion of principal groupoid bundles. So you have to define all this, but it's more or less similar than the example of quotient stack we just defined, okay? So we can define a differential stack in that way. And the second property is that any two Lie groupoids are going to define the same differential stack if there exists a weak equivalence of categories or is Morita equivalence between them in this context. So it's important to see or to say that if you want to define something on differential stacks in a way that you are going to use the Lie groupoid, you need to check first that these objects are Morita equivalent for these Lie groupoids, okay? So when you want to define cohomology, you need to define cohomology that are Morita equivalent with respect to the Lie groupoids, okay? In that way, for example, we can define the rank cohomology the idea of this cohomology is consider a differential stack with his atlas, and then the Lie group point associate, and then the nerve of that. So you are going to have a nerve, a simplicial smooth manifold, and with that you can apply the differential forms in this nerve, and you are going to get a double complex. This double complex are going to have as differentials the exterior derivative, the RAM differential, and the one that comes from the simplicial structure of this nerve. The simplicial structure of the nerve, that means that you are going to alternate sums of the pullbacks of the faces from here. So we are going to say that this thing is the RAM cohomology. One important thing about this is that these cohomologies are really, they have a really close relation with the pathometric realization of this nerve. So in general, the motility type of a differential stack is going to be given by the pathometric realization of the nerve associated to all these constructions that we made. Okay. So now we have cohomology, we have differential stacks. So now we want to know how it works, the concept of actions of these differential stacks. Okay, so this notion of an action on a stack was given by Romagni in the context of algebraic stacks, and he developed more things in the context of topological stacks. So an action of a Lie group G on the stack M is going to be a morphism of stacks, such that it's going to give us a weak definition of an action. That means that it's going to have this diagram is going to be accomplished in the setting, but it's going to be up to isomorphism. So if you go to this path and you go to this path, you are going to get something that is up to isomorphism equal. That means this alpha here. In a similar way, you are going to get something for when you are using just the identity. So the identity is going to leave everything in the same place up to isomorphisms. Okay, and we are going to say that if you have a stack with an action, this is going to be a G stack, as usual. In a similar way as in the classical case, when you have an action on a smooth manifold, we have equivariant morphisms. So you have two G stacks in here, and this F is going to be well behaved with respect to the actions. Okay. Now, since we have the notion of an action stack, we can define the quotient stack in a very similar way that we described before when we were working with a smooth manifold X in here. How we are going to do the quotient stack is going to give us Lie group points for any smooth manifold T, where the points or the elements of this group point is going to be given by pairs of principal T-bundles and equivariant morphisms, of course, in the context of we are talking about, so in stacks, no? And the morphisms between them are going to be just morphisms of principal T-bundles and well behaved with respect to equivariant morphisms. Yes, that's the thing that we are saying here. Okay, so my research then was try to find equivariant cohomology for these quotient stacks. Okay, so the idea was try to follow this way to thinking, and this is going to be discussed a little bit more in my second talk. So the idea is trying to find an atlas for this quotient stack. Secondly, try to describe how is that Lie group point associated to this stack, and then try to compute the motility type. Okay, so that's the idea. And what we got from this was that if we put more restrictions in the atlas, when we have a G stack here, we can get we can recover the Borel model that we described in the classical case. Which restrictions are there? Well, we are going to ask that X has an action and this atlas has to be an equivariant morphism here. Check that, for example, in this equation, when M is a smooth manifold, all this pattern realization is going to collapse on X, and you are going to get again the Borel model. So in this way, we define the equivariant cohomology as the cohomology of the quotient stack. That's something that is nice because it looks like more or less the idea to try to find a cohomology for the quotient space, no? At the beginning. There are more models. Yes, there are more models. This was given by my ranking, but a simplicial smooth manifold.
Luis, just a 5-minute warning for you.
Okay, thank you. And the idea is just applying the equivariant forms for each element in the simplicial smooth manifold and consider the extra structure. That means that we are going to consider the differential that comes from the simplicial structure of X, and we are going to use this differential. This is the Cartan differential plus the differential associated to the simplicial structure. What is the nice thing about this is that these complex are going to compute the same cohomology as the quotient stack. So we are going to have something like this as the Cartan theorem. That's something that we got there. Okay. What I'm doing now is something related with all these things. The first thing is find out joint work with Frank Neumann, and the idea is try to classify isomorphic classes of G-equivariant principality models, as well with G-equivariant Gers with Banti. These theorems were actually in the classical case of smooth manifold given by Berlinski. So what we are trying to do now is trying to get these more general results in this context. And as well, with Professor Christian Ortiz and his student James Simeao in Sao Paulo, we are trying to conceive an equivariant cohomology of two groups. And that's something that we are doing now, and actually that's what I want to tell you for now. Thank you so much.
Okay, thank you very much, Luis. Let's everyone give Luis a good round of applause. Okay, excellent. So we are ahead of schedule, but not too much. So now we're moving on to the parallel session part of our conference. We're going to open breakout rooms, as I mentioned before. I encourage everyone to take like a 5 to 10 minute screen-free break just to rest your eyes before we continue. So I imagine that all the parallel talks should start roughly maybe 5 minutes past the hour, something like that, just so that everyone is rested and stretched. Yeah, stretching is also a good idea, and maybe a cup of coffee or tea. Okay, so I'll open the rooms now. Okay. Oops. So if anyone is in the main meeting room right now and you are unable to join breakout rooms, you don't see the option. It might be that your version of Zoom is old, you haven't updated, which is okay, because then just let us know and we'll manually put you in a breakout room.